As I promised in a previous video, I'm now going to solve Schrödinger's equation, the time-independent Schrödinger equation, for a one-dimensional system to obtain the eigenstates, the eigenenergies, and eigenvalues. In a sample case of square quantum well, symmetric square quantum well. Okay, and for that I'm going to use a very simple application for like one of these spreadsheet applications like Google Spreadsheet or LibreOffice Calc or the Microsoft Excel. So if you didn't watch the previous video about shooting method, I recommend you to watch there, and you click the like button if you like it. But there you'll have the explanation for what I'm going to present here. So the actual calculations. So here what I'm going to do is to put all those equations in the software and see how the wave functions show up and how we obtain the eigenenergies, etc. Okay. So just to make a review of what we did before, what we are going to solve here is the time-independent Schrödinger equation in one direction. The direction here is x, the x-axis. So the potentials, we made it in a dimensionless form. So energies are divided by the readback energy, the distances and space variables, the spatial variables, they are divided by the Bohr radius. So in the end, you find this equation that is in a dimensionless form. And since we are dealing with a symmetric quantum well, we just need to solve it for the positive part of the x-axis. The negative part of the axis will be obtained if you, let's say, if you chose an even wave function, then you just reflect the wave function to the left part, and then you can repeat it there and you get the whole wave function. Or if it is an odd wave function, then you just multiply it by -1 and put it on the other side, the same function there. Okay. So, and as you know, there is a way to prove that if you have a symmetric quantum well or symmetric potential in general, then the wave functions will for sure be either even or odd with respect to x equal to 0. Okay, and so the method was involved like discretizing the x-axis into small steps like this, and the steps, they have a size delta x. And now the derivatives are divided, they are redefined like this. This is what we call finite difference method, right? And in the end, you get some some recursion pair of equations that allow you to obtain the wave function and its derivative. And you obtain them, for example, for i+1 point in your axis, using the values that you have for the I point in that axis. So in this case, for example, if I define the derivative and the function itself at I equal to 1, then I use psi of I equal to 1 to obtain, and the derivative, right? To obtain psi at I equal to 2, and then I use that to obtain the derivative at I equal to 2, and then I use the derivative at I equal to 2 and the wave function at I equal to 2 to obtain psi in I equal to 3, and so on and so forth. So in this case, we get the wave function over the whole axis. And for that, I have to choose an energy, right? And if you choose the wrong energy, if you choose an energy that is not an eigenstate of the system, your wave function, of course, it will exist. You just like you input these numbers there will be a wave function there. But the problem is that this wave function does not obey what we expect as the boundary condition. You see that the wave function will diverge. Okay, so you need to change the energy until you find a wave function that does not diverge. That's the method. Okay, so now let's go to the software then. The one that I'm going to use here is the LibreOffice Calc, right? But if you use Microsoft Excel or Google Spreadsheet, I guess Google Spreadsheet also would work, more or less the same. So what I did here, I already filled some of the cells in my spreadsheet here with some stuff, that's going to be useful during the calculations. As I said, for example, I need the Rydberg energy and the Bohr radius, and that's why they are here already defined in angstrom and in millielectron volts. So these are the numbers. So delta x, I'm going to use this thing. So as I'm going to use delta x, for example, in this expression, then it's good to have, so here's delta x, for example, or here. So it's good to have delta x as a cell in this code, so that it refers to that cell every time it needs it. So here what I did was I chose 0.1, so don't mind this, there's a comma one, that's because it's in Brazilian Portuguese, the language here. So it just, when you look at 0.1, just ignore the comma and replace it by a dot. So this is like 0.1. So 0.1 divided by B3, as I said, this would be B3, cell B3 would be the Bohr radius. So this is a mesh that has delta x equal to 0.1 angstrom divided by the Bohr radius. That's what gives you this number that you see here. The energy, right now, this is just a guess that I made here. And you see the guess here, I'm already dividing it by B2. And what is B2? That would be the Rydberg energy. So that's also fine. It's in the correct unit, right? Then there's something else I already prepared here, is the x-axis. So what I did for the x-axis, it starts at 0. The next point in the x-axis is the previous point, you see A6, plus the cell B1. So you see that there are these dollar signs here. This is what makes this thing fixed, at least in this language for LibreOffice. Okay, so I guess there will be something similar to that in Excel, Microsoft Excel. So you see, once you obtain a number here for A7, then you repeat the formula for A8, A9, and so on and so forth. You see that these are the cells, you can check them here. These are the formulas that I put in the cell here. So this is how you obtain this axis here, like that. So this one depends on the previous one. So this is A15, it depends on A14, and so on and so forth, right? So now I created this axis with, I think here I use it something like 400 points. Yeah, it looks like it. So if you scroll down here, it goes all the way to 400, you see? Almost 400, because I started already at A6, I think, right? So the other column I already defined, it was the potential, because this is also something I'm not calculating. This is something I'm giving to the code, right? I'm saying the potential is 0 everywhere until it reaches the 157th point in my grid. And this one, if you multiply by the 0.1 that I have for delta x, that would be something like 15 angstroms. Okay, this is 157 because I started at the sixth cell in the spreadsheet. You see, I started from here. So this is like 150 points, which means that I have something like 15 angstrom of width with a potential that is 0, from 0 to 15 angstrom. That's the idea, okay? So, and this is just half of the quantum well, therefore this quantum well has 15 to the right side, to the positive side, and 15 to the negative side. So it's like this, right? So I have 15 here, this is what is there in the code, but I also have 15 here. So in the end I have a quantum well that has 30 angstrom inside. And from here on, the potential for x larger than 15 angstroms, I use a number that is 4,000 millielectron volts, so that is 4 electron volts, divided by B2. And what is B2? That's the Rydberg energy, right? So here is B2, that's Rydberg energy. So this is the height of my quantum well, okay? So what I'm saying with all this calculation here, and then I just repeat the formula everywhere, what I'm saying here is that this quantum well has 30 angstrom of width and 4 electron volts of height. Okay, that's what I'm saying here. Now let's solve Schrodinger equation for that. So how do we solve it? When I have psi, I'm going to start with the even solutions. So I'm saying that psi at x equal to 0 is 1. Derivative of psi at x equals to 0 is 0. That makes even wave function, right? So if I want to calculate the next point, the wave function and the next point, how do I do it? I use the previous one, that's why I'm writing here b6. I multiply by delta x and by the derivative, which is c6. See? So with that, I calculate it, and that's it. And in this one, how do I calculate the psi prime in the next step? That's what is done here. So this is the one in the previous one, delta x v minus e psi of the previous step. So how do I do here? I get c6, so it's psi in the previous, the derivative of psi in the previous value. Then b1, that's the delta x. This 6 minus E1, that's the energy, right? This 6 is the potential minus the energy multiplied by B6, which is the psi at that point. If you verify this formula, that's exactly what you get if you want to put this thing in that cell. So now you just get this cell, you put Ctrl C and just repeat this cell everywhere. Let's see. Looks like, let's see if it's going to update it automatically, because it will depend on the derivatives, and the derivatives I still didn't define, right? So it may be that when I do it like that, there will be some wrong numbers right now, because it's 0 everywhere for the derivatives, right? Now I'm going to do the same for the derivatives. I'm going to repeat this formula all the way down here. So let's, did I put Ctrl C? Okay, Ctrl C in the formula, and now I will repeat the formula everywhere here. Let's see, okay. Now, this figure that I put here, this is already a plot of, if you look at here, this is column, let me see, yes, column B. So that's the wave function that I have already, psi, which means that you see that this wave function is going down, it's going over the 0 axis here, and this means that it's going to diverge to minus infinity, which means that I chose the wrong number here. So 76.5 may be too high for that. So let's try 74. You do 74, it gets a little bit different, you see. Now let's try 70 or 50 something. Let's see. And it's still bad, you see. So let's reduce even more. 20. Oh, now it diverged positively. So 20 is too low. So let's try 30. Then it's getting better. Let's try 40. Oh, that's too much. So it's between 30 and 40. So let's try 31. Too much. Or actually too less, sorry. Then 32. It's getting better. 33. Better. Let's try already 35. Yeah, it's getting better and better, right? Let's try now 37. Then it's too much. So it's between 35 and 37, right? Let's try then 36. Then it's too much. Or it's too less, I mean. 36.1. Oh. 36. I cannot use points, sorry, that's in Portuguese. So 36.1, which is the same as 36 plus 0.1, okay? So that is almost there. Let's try 36.5. Then it's too much. So let's try now something in between. 36.4. 36.3. Then it's too less. So 36.35. It's getting better and better, you see? 36, 37, 38. Then it's too much. So it's between 37 and 38. Now let's try 37.5. Then it's too much already. So let's try 37.3. 371. Then it's too less. So it's between 371 and 373. Let's see, it's 372. Yeah. 3721. So you see, I'm getting it more and more precise, you see? And that's what I'm trying to do, is trying to get this wave function to come here and converge all the way to the 80 here, which is the end of my grid, okay? So if I don't choose exactly the correct wave function, there will be this thing, this is spurious, I know that this is not correct, but the energy cannot be too different from this thing that I already found here. That's the point. So I already found the energy. All I'm doing now is just to refine it. So if I want it a little bit better, then I can do like this, but now I know that it's between 1 and 2. Let's try 1, 5. You see that it's getting like a huge amount of numbers in the accuracy here, right? So this is all about accuracy now. So I'm almost in the correct answer. So this is, instead of 6, let's put 55. That's too much. You see, if I am patient, if I do this with patience, then I can do it in a very high precision. See, I'm getting closer and closer to the 80 here. So if I'm saying that, if I want to say that this is already precise enough for me, then I can say that, okay, that's the energy, that's fine. So that's all I want. Well, actually, can we verify that this is, if this energy is correct? Well, there is a way to verify that, right? Because this quantum well is very high in energy. So there is something that I could do already. I could use the analytical solution for a quantum well. So I could try to say that this is a quantum well that is an infinite potential quantum well. In that case, the energy, I could know more or less how it is. The energy of a quantum well is the Rydberg energy, so that would be B2, multiplied by the Bohr radius squared, so that would be B3 multiplied by B3, right? And then pi squared, I could put 314, and now this B2 will cancel the one in the denominator. But now this is like Rydberg energy multiplied by Bohr radius squared, and I have to divide also by the size of the quantum, the length of this quantum well, and I said that that's the length squared, right? So I have to divide by 30 and by 30. That should be a very good guess on the energy. So I'm saying that the energy of this quantum well should be Rydberg energy multiplied by A0 squared, n squared, pi squared over L squared. Actually, if you want to convert the solution to more like some constants that are easier to understand, maybe you could try to say that E is actually h bar squared, then n pi over L. Here's 2 times the effective mass. In this case, it's just the electron mass, and this thing is squared. So that is more or less an approximation for the solution that I'm looking for, right? So that's why I wrote it like that. Let's see if this is a good guess. I do it like that, so that's not perfect, but let's put some number in front of this here. Let's say 80% of this thing. Oh, sorry, I cannot use point. This has to be comma. Okay, so maybe 80% is too less. let's put 90%, then it's too much. Let's say 89% or 88%. Okay, so it looks like if I try this infinite quantum well solution, I would be with an error of something like 10%, almost 13% of error, because the energy that I get here is something around 87% of the one of the infinite quantum well. But this is not an infinite quantum well, right? I mean, I'm using a quantum well that has a finite size, finite height, right? But maybe I could get maybe a little bit better number if I have an effective length. Let's say instead of 30 angstrom, we have 31 angstrom. In this case, maybe I could go to 90%. What I'm saying is that effectively, I'm saying that I think this quantum well has 30 angstrom of length, but actually what it has is more like 31 angstrom of length. So you see, it gets better when it's like that. Now I have a precision of like 93% more or less of the infinite quantum well that I have here. So I'm doing this just as a way to show you that the solution that I get is more or less expected for a quantum well like that, right? So the number is not wrong. Okay, so let's try to remember which number we used here before. Maybe I could do Ctrl-Z several times to see if I obtain that number again. Okay, that was the solution that I had before, right? Now, I said that I could also do the same for excited state, right? So what I have to do now is to try to obtain higher numbers here that also make the wave function converge to zero here in the same way I did here. In principle, I could just like increase this number all the way up, but I already know that as this is a quantum well, if this is n equal to 1, the next even solution has to be 9 times this one. Now I have to look for the one that is n equal to 3, that gives me an energy that is 9 times larger than the one of the ground state. So let's make an educated guess here that is more or less like 9 times 36. So that would give me something like, let's start with, so here is the number, and now I see that this number, let's see, if we do it a little bit smaller, let's start with this like that, then it's too less. So let's say 26, too less, 27, then it's getting better, you see? Now 27.5, then it's too much, so it's 27 point, let's say 2, it's too much, 0.1, 0.01, 0.001, and it's too less. So I could put 0.0005. So you see, I'm just changing the numbers here until I get what I want. Put a 9 here, still too less. So this is actually 1, that should be fine. Or maybe 2, 3. So 4 is too much. So now I can try 35, for example. And then if I go on and on, I find another energy, which is the energy of the second eigenstate that is still even in the x-axis. How about the odd solutions? The odd solutions would be, let's say that I start with this number here, psi1, and I say that psi1 is equal to 0, and this one is 1. What does this give me? This is a situation where the wave function starts at 0 and the derivative is 1, which means that this wave function is odd, right? Now, the energy for the odd state should be more or less like 4 times the one of the ground state. So let's make an educated guess again. That would give me something around 135 maybe. Let's try. It seems too much, or too less maybe. And then 150 is too much because it now crosses it here. Now let's try 149 for example. Actually, let's change the axis here so that we can see this thing a little bit better maybe. So I've changed the axis like this. Now it's better to see more or less how this wave function will converge. So 149 seems to be too much. Let's try 148, 145. So 145 is too less. Then 146 is too much. So 45.1. Then 45.2. Then it's too much, so then it's something around maybe 3. Okay, so you see I'm getting more and more precision for this first eigenstate, for the first odd eigenstate of the system, right? And then the wave function is getting better and better like that. So you see I already have a wave function that goes up and down and then it converges until some precision, right? Now if I want the eigenenergy only up to this precision in energy, then it's done already. So so now that I changed the grid, we can also take a look at this previous energy state that I got for the system when I had the even one, the first excited state of the even system. So let's try again the first excited state of the even system. So if I want to see that again, let's put it 1 here, 0 here, and then the wave function looks like that. And I already saved it here, the number that I had before that gives that energy more or less. That would be something around 327.33. So that's what they tried, and you see the wave function now it looks like this. It has some wave and then it goes up to here and it converges more or less up to some accuracy. Maybe I could change these numbers here so that we can get something more stable. You see, now it converges even better, and the wave function has a node in this point here, just as we expect for the first excited state of an even wave function. So that's it. That's how you use LibreOffice to solve Schrodinger equation. With that, if you go on and on changing these numbers here for the boundary conditions and changing the energies here, like guessing different energies, you obtain the whole spectrum of the system just looking at wave functions that converge up to some accuracy here. And that's it.